Okay, we are moving into the acids and bases. We're going to go into this in more detail in class. We're going to work some problems in class. This is going to be really important to you, again, for any of the medical fields. All right, you need to remind yourself about acids and bases. I'm going to spend a minute reminding you. Electrolytes are molecules that have ionic bonds between them, not shared electrons. One gives, one takes. They have a very weak bond. 3 categories: acid, base, salt. If you put any of these 3 groups into a water solution, they will dissociate. The ionic bond breaks. One of the guys gets the electron or electrons, and the other guy that was donating an electron loses it. And so the ionically bonded electrolyte molecule splits into ions. Alright, so if you look at the 2 solutions on the right, you've got a hydrochloric acid, HCl solution, HCl put into water. On the right you've got carbonic acid put into water, H2CO3. Look at the HCl. You put it into water, the bonds break between hydrogen ion and chlorine ion, and you get 2 kinds of ions. You get the cation, positively charged hydrogen. You get the anion, negatively charged chlorine. All ionic bonds are broken. Everything is ionized. Everything's an ion. Now, look over at the carbonic acid, and you see there's some ions. Some of the molecules have split, dissociated into ions, but other molecules of carbonic acid have stayed together. You don't have complete ionic bond break. You don't have complete dissociation. HCl is a strong acid. Carbonic acid is a weak acid for the exact reason I just mentioned. And you can see it right in front of you. It has to do with how much dissociation into ions. Strong bases, weak bases, they work the same way. I just happen to have 2 acids here, a weak and a strong acid. Strong acids are at the low end of the pH scale, 1, 2, 3. Strong bases are at the high end of the pH scale, 13, 14, 12. Weak acids are more towards neutral, 6, 5. Weak bases are at towards the neutral middle of the pH scale, 8, 9. So preferably you would much rather have, your body would much rather have weak acids and weak bases than strong acids and strong bases. Keep that in mind. It's going to really help you when we talk about buffering and things like that. Alright, let me remind you about pH. There's the formula. It's a concentration of hydrogen. It's the log number of that concentration divided into 1. That number is turned into the pH scale. Alright, pH 1, pH 5, pH 9. Alright, each of those numbers on a pH scale is a 10-time difference. If HCl, let's say, is a pH of 2, and carbonic acid, no, let's use something else. The acid in yogurt, okay? Yogurt is kind of acidic. We take a pH of it, let's say it's 4. So we're comparing the pH of HCl to the pH of yogurt of 4, 2 to 4. From 2 to 3 is a 10-time difference. From 3 to 4 pH is a 10-time difference. You multiply those two 10-time differences and you get 100. 10 times 10. Now, let's compare hydrochloric acid to carbonic acid. HCl, let's say pH 2. Carbonic acid, pH 8. We're going from 2 to 8. 2 to 3, 10 times difference. 3 to 4, 10 times difference. 4 to 5, 10 times difference. 5 to 6, 10 times difference. 6 to 7, 10 times difference. 7 to 8, 10 times difference. That's 6 10-time differences. That's 10 times 10 times 10 times 10 times 10 times 10. That's 1,000 times 1,000. That's a million. Million-pound difference in acidity or alkalinity. All right. Blood pH, you know this already. You do not have much leeway. 7.35 to 7.45. You get less than 7.35, you're in acidosis. You drop down to like about 7, you're dead. Your blood pH never goes down to 6 or 5. You'd already be dead. Who cares by that point? You get up above 7.45, you're in alkalosis. You get to about pH 7.8 or 8, you're dead. We don't care if your blood pH is 8.5. You're long gone by then. All right, acids. The bigger problem are the acids, not the bases. You make all these acids in the Krebs cycle and glycolysis. Bases are made in protein breakdown, but acids are the bigger problem. So acidosis is a more common situation. Now, where do these acids come from? 3 categories. Let's go organic acids. They have carbon, they have hydrogen bonded to carbon. You've seen these before. Ketones, keto acids, lactic acids, well, trying to think what else. Pyruvic acid, all the acids of the Krebs cycle. All right, then we've got volatile acids, and these are the acids that go into the atmosphere. You know where I'm going. I'm going with carbonic acid, which is eliminated from the body as CO2. That's the only one in that category. Then we've got the fixed acids. They're sometimes called inorganic acids, although carbonic acid is an inorganic acid too, even though it's got carbon. No, I'm wrong. It's an organic acid because it's got hydrogen bond to it. The fixed acids don't leave a solution. Sulfuric, phosphoric, hydrochloric acids. Okay, so keep them in mind. All right, so we're going to look at 3 different ways that acids and bases are kept in balance. All right, chemical acid-base buffers. You've seen this before. Here's your formula. Let me take you through it. The cell undergoes aerobic respiration. It makes carbon dioxide. It reacts with water. The 2 of these form carbonic acid. This happens in all cells of your body. Now, this carbonic acid is kind of a pivotal role. It dissociates, because acids, that's what they do, they dissociate, into hydrogen ion and bicarbonate ion. So, I mentioned that carbonic acid plays a pivotal role. These are reversible reactions. See this? It can go either way. See this? It can go either way. So, if your blood pH is more alkaline, then you may have a shift that way or that way if it's more acidic. So this guy can affect which way we go. We'll talk more about this in just a second. Remember, the CO2 is expelled from the lungs. So if this carbonic acid, get rid of all that, shifts that way, back down into CO2 and water, then this can go right out of the body. Alright, it's going to shift your pH upward. Okay, you're getting rid of this, and you're getting rid of this, so your blood pH goes up. On the other hand, well, I don't want to get that far into that. Okay, we'll get back into that when we get into breathing. Alright, so there are different acid-base buffer systems. The main one we're going to talk about is the bicarbonate carbonic acid one. So let me just give you some basic chemistry here. Reminder, this is a strong acid. I already introduced you to it. This is sodium bicarbonate. It's a weak base. You know it's a weak base. You know it's a base because you got it in Tums and Rolaids and what do you call that stuff? Baking soda and things like that. All right, weak base, strong acid. Think about what's going to happen here. Bond breaks between HCl. Bond breaks between Na and bicarbonate. Again, these are ionically bonded. This hydrogen is going to combine with this bicarbonate right there, and you are going to get carbonic acid. The remaining Na, the remaining Cl, NaCl. So what we have done is we've taken HCl, which is a strong acid, and we have turned it into a weak acid. In other words, here's your pH scale. HCl, okay, here's neutral. HCl is down in this area. By turning HCl into a weak acid, we have shifted its pH more towards neutral. That's less damaging for cells. Okay, now the second guy you see below, strong base, NaOH. This is sodium hydroxide. You would find it in various sink solutions to get rid of hair and clogs, Drano, things like that. All right, strong base. Carbonic acid, H2CO3, weak acid. Ionic bond breaks. The ionic bond here between the two H's breaks. This sodium is going to react with the H, the remaining H, CO3, and it becomes this weak base. This OH, the remaining H, water. So what we've done is we've taken a strong base, turned it into a weak base. Again, on the pH scale, here's NaOH, strong base. We have shifted it down into this pH area by turning it into a weak base. Not as bad for the cells. Okay, other kinds of buffers. By the way, that buffer system I just talked about, again, remember bicarb and carbonic acid, they shift back and forth. Major buffer for blood plasma, for blood. All right, other buffers, phosphates. Really important in pH of urine. There's a monophosphate. There's a with one hydrogen, two hydrogens. It shifts back and forth. You always have two buffers. Protein buffer. Okay, you see a picture of it in the forefront here. Here is an amino acid right there. Or I could have a lot of amino acids. It doesn't matter. Anyway, depending on pH, whether your solution is alkaline or acidic, this amino acid or the protein, because a protein will have a carboxyl on one end and it'll have an amino group of another amino acid at the other end, will vary to act as either a base or as an acid. An amino acid can act as a buffer. Protein buffers are the most important inside cells. Buffering changes of pH inside cells. Good example, hemoglobin is the major protein buffer in a red blood cell. We covered that before when we were talking about gas transport. Okay. Here's a layout of the buffers. Alright, so here's the most important thing to remember. Bottom left. Chemical buffers temporarily tie up acids and bases. They are for short-term control of pH changes. If there's a big pH shift, chemical buffers can't control it. Let me say it again. They are for minor shifts of pH, not too devastating, and they only do it for a short amount of time. If there's some underlying big problem causing this pH shift, it's going to fall to your kidneys or your lungs to control it. Chemical buffers can't do it. Alright, so some things to think about as we go through further along into the acid and base control. I've already mentioned acid is the bigger problem. Carbonic acid and bicarb are the main buffers in blood. Changes in CO2 affect hydrogen ion because CO2 contributes to carbonic acid, and again, acids release hydrogen ion. Although hydrogen ion makes things more acidic, bicarbonate makes things more basic. Remember, your kidney can control these two things in your blood. We already talked about how the kidneys can be involved in pH control of blood. The lungs also have a job here because the lungs eliminate CO2 and can control partial pressure of CO2 in your blood. And remember that that's tied to carbonic acid and pH of your blood. Last thing, we're going to be talking about kidneys and lungs a lot here. These two organ systems, two organs, work together to try to keep your pH balanced. Alright, so let's shift over to breathing. I kind of already gave you a little bit. I didn't mean to get into respiration, but here we go again. There's the formula. So, when you hyperventilate, you are blowing off more of that going out. And so your blood, PCO2 goes down, and your blood carbonic acid goes down, and your blood pH value goes up. So hyperventilation is going to tip you more towards alkalosis. Now your breathing affects that. If you slow your breathing down, instead of hyperventilating, you now slow breathing down. That allows CO2 to accumulate. Your PCO2 goes up, your carbonic acid goes up, your blood pH goes back down. Flip side with hypoventilation. Think about it. Okay. Kidneys. Remember, kidneys can control hydrogen ion going from the lumen of the tubule back into the blood, or the other way. That's what you see on this picture. Far left, in yellow, lumen, where the urine is. Far right, blood. So you can see hydrogen ion right in the middle. The kidneys can secrete more hydrogen ion. Okay, here's hydrogen ion right there. And it can shift this way, going out, or it can leave hydrogen ion in. You can see where this is going to affect blood pH. Your kidneys also can control this bicarbonate. Shift more bicarbonate out. Actually, you can shift it right out of the blood out. Or your kidneys can shift more of that bicarbonate in to buffer acidity. Again, here's a look at acids. I knew there was one acid I forgot. Uric acid. Okay, well anyway. So we've kind of talked about that already. Alright, so some key things here. Again, here's the buffer system I talked about. Temporary, but very quick. Lungs. Pretty quick, It does it by controlling the CO2. Kidneys takes longer, but it's the most important. I mean, because you can really sway blood pH with hydrogen ion and bicarbonate control from the kidneys. Okay. So, oops. We're going to move into problems here. The area that I'm in, by the way, is called ABG. You'll learn that very quickly in nursing. It stands for arterial blood gases. Anytime you're talking about acids and bases and things like that, you're in an area called ABG. Okay, death. I haven't talked about symptoms here. When you are in acidosis, which is that situation, less than 7.35, you are going to have depression of the CNS. I mean, the extreme would be death, but also there's less extent. You got coma, depression, lethargy, can't think, blah, 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 blah. You go the flip side up into alkalosis. So now we're at over 7.45. And you've got hyperexcitability of the CNS. Muscle spasms, everything is up. And of course, cause of death is cardiac arrest, whereas in acidosis, CNS depression, because blood acidity also is going to affect the brain. The other thing you need to remember as we go through here is generally, if something is going on in your body causing an imbalance, another organ will try to compensate. If you're blowing out too much CO2, if you're hyperventilating, you're blowing out more CO2 than you should be, and your blood begins to go alkalotic, that is basic, your kidneys are going to try to hoard hydrogen ion in your blood to drop your pH back down. So your lungs are the cause of the problem because you're hyperventilating, but your kidneys are going to try to compensate. That's what I mean by compensation. The flip side is true also. If your kidneys are the source of the problem, then your breathing will be affected because your lungs are trying to compensate to keep your pH back in balance. Now, if you're young and you're going through these problems, you can probably compensate. But if you're an 85-year-old, I don't know, man who's got emphysema and diabetes, I don't know, let's throw in whatever else you want, and you've already got organ problems to begin with, you could already have some kidney damage, and you're obviously going to have emphysema from your lungs, then when you tip over into acidosis or alkalosis, the other organ system may not be able to compensate very well because it's already, halfway gone, and you've got uncompensated imbalance. And that's obviously more life-threatening. Compensated means your body's going to try to kind of keep it in balance. Uncompensated means it's like a snowball rolling downhill, gathering momentum. Okay. All right, so let's go on. All right. So here's a simple little mnemonic device, I guess, to help you if you can't remember a pH scale. You ought to know it by now. Low pH values. Acid. Acidosis. D for down. pH low. Alkalosis. High pH. The K kicking the pH value up. Whatever works for you. Okay. So, reminder, look at the second bullet. CO2 is the respiratory component in acid-base balance. Your lungs control it. Bicarbonate is the renal component in acid-base balance, controlled by the kidneys. I've already mentioned compensation. If it's the lungs that are the problem, kidneys try to compensate, vice versa. Um, okay. Another look at compensation and the two organs involved in compensation. Let's see, was there something below that? No. Okay. All right, so let's go acidosis first. Definition, you know what it is. It's excess of acids, or it could be a loss of bases. Now, excess of acids, you're too slowly breathing. You got too much CO2 in your blood. You've got too much carbonic acid in your blood. Okay, you understand that. How about loss of bases? Where do you find bases in ECF? Intestine, right? Small intestine particularly. Basic. If you have severe diarrhea, you're going to be losing basic chemicals from the ECF. That will affect your blood pH and put you into acidosis. Now, I'm just giving you two examples here. There's respiratory acidosis. There's metabolic acidosis. Respiratory acidosis is where your lungs are causing something, a change in breathing pattern, that causes too much, too little carbonic acid. In the case of respiratory acidosis, it's causing too much carbonic acid. Like a slowdown, too slow breathing would be a cause. Or if you held your breath for an abnormally long time, you can put yourself into respiratory acidosis. Metabolic acidosis, I mentioned diarrhea. It could be due to kidney problems like renal failure. Remember? Uremia, excess uric acid, urea. Okay, acidosis goes along with renal failure. You could be diabetic. What's the acid that accumulates in diabetes mellitus? Ketones from too much fat breakdown. All right? You know what the symptoms are. Again, they're a little bit different, respiratory versus metabolic, but generally it's depression of the CNS. Again, think about compensation. If you're in respiratory acidosis, you got too much carbonic acid, too much CO2, your PCO2 is too high, what will your kidneys do? Your kidneys will retain bicarbonate. Bicarbonate is a base that tries to get your blood pH back up again. That's the kidneys compensating for the lungs. Okay. Treatments, not really going to get into that. You'll get into that in nursing. But obviously, the first thing off your head you should think of is you might want to give a base, a bicarbonate solution. Alkalosis, respiratory and metabolic. I've already given you the example of hyperventilation. You're blowing off too much CO2, your PCO2 goes down, your carbonic acid goes down, you tip over in towards the high end of the pH scale, more than 7.45. Metabolic alkalosis. Interestingly enough, one of the number one causes of it is over-ingesting too many Tums, Rolaids, things like that. People that have cardiovascular problems very often take a lot of antacids. Antacids, remember, are weak bases, like bicarbonate. You can put yourself into metabolic alkalosis. Remember hyperexcitability of the nervous system and the heart and muscle and all that. Treatments. You could give an acid solution to counteract alkalosis. If it's respiratory alkalosis, you could have the person breathe into a paper bag, right? That raises your CO2 and your PCO2 and your carbonic acid. We're going to get into how you work these problems, just to give you some experience, because you're going to have a lot more of this in medicine, but I just want to expose you to it so you know how to do it, or that at least you're familiar with it when you see it again. Not important. Down at the bottom you see pH. You definitely know that. But there are normal limits, high and low, for PCO2 and normal limits for HCO3, your bicarb. You don't need to know those two. 40 OPT, by the way, means optimal. But if you're going to work any acid-base problems, then you have to know those high and low limits. And I'll go over a mnemonic device that helps you to figure out whether somebody is in acidosis or alkalosis, and if it's compensated or not. Here again is another mnemonic that I found showing causes of alkalosis and causes of acidosis. You can stop this if you like and go over it. Here's, I think this is out of your book, I'm not sure. I steal a lot of pictures that I like. So definitions and causes. And again, feel free to stop this. Okay, so last thing. Problems. We've talked about some of this already. Infants have got way more water than adults. And when there's a water imbalance, it can really affect them. That, of course, affects electrolytes. Remember also they need more nutrients. They have more waste. So obviously kidneys are all important in newborns. Remember that they don't have a countercurrent multiplier process for a couple of months. They have no way to concentrate their urine. So they're putting out dilute, voluminous urine. They can get into an acidotic state if there is during labor and they can't get out, long labors, or they're moving around. They get into fetal distress, lots of muscle contraction, right? They go into a lactic acid fermentation, or their muscles do. They're making a lot of acids. They can get into metabolic acidosis. Old age. They have less water content than like a 40-year-old. But you still got the same problem. With less water, when you lose water, you can put yourself into an imbalance also. So you got the extreme ends. Infants and old age are problems in water balance. And when you throw in, for the elderly, there's a natural loss of kidney function and lung function, as well as brain function and everything else as you get older. And when you put yourself or get yourself into acidosis and alkalosis, and you don't have that other organ to compensate, it's a real problem. And that is it for this chapter.